Welcome to the class meeting 11 of the EC 202 Introduction to Probability and Random Processes. Last time when I was talking about this one as a function of some unknown number A, I said that the left-hand side could be any shaped function, but it was totally wrong under the assumption that the first and second order non-central moments exist. This function becomes a quadratic function of A, so it is always parabolic shaped curve. So it's differentiable, and you can find the value of A as the conditional mean of the random variable X. Anyway, so last time we started to study the situation like this. So here goes our random number generator, and here is a function that maps the input to output deterministically. And we have two cases. The first one is that we want to characterize the distribution itself, and apparently looking simpler problem is to find the expected value of y. And we are working on this problem first, and then we are going to move to the first problem, hopefully today. And what was the definition of expected value of y in this case? Of course, we may use measure theoretic definition like this, or we may use the induced probability measure, or we may use, just a second, we better have y here. We may use the CDF. And if PDF, PMF exists, then we have two more formulas. So using the definition to find the expected value of the output, we need to derive, for example, the induced probability measure or the CDF of the output. However, we've seen that there is so-called the fundamental theorem of expectation. And what was that? The fundamental theorem just says that since capital Y can be written as G of capital X, then we may just use the induced probability measure of X, the CDF of X, or PDF or PMF of X without deriving these functions. Got it? And how did we prove that? Actually, if we use the definition in measure theoretic sense, this so-called fundamental theorem of expectation is a trivial result. So if we do not use the measure theoretic definition, it's rather complicated to prove the fundamental theorem. So some textbooks show the proof assuming the random variable X is a discrete random variable. In that case, we can easily prove the fundamental theorem. Anyway, so after we have derived or have seen the fundamental theorem of expectation, what did we study? We studied so-called the moments. So we wanted to talk about the expected value of a random variable X raised to the power of n. Sometimes we take the absolute value before we raise it. Sometimes we subtract the mean and raise it, or sometimes we subtract the mean, take the absolute value, and then raise it to the power of n. And the first two are called non-central moments, and the last two are called central moments. And the second and third one are called absolute moments. Got it? And among these many moments, the famous one is what? The first order non-central moment, which is called the expected value of random variable x, or mean ensemble average. And the second one is the second important thing is the second order central moment. And this is called the variance over random variable x. When we define these moments, I recommended you to have a habit like a Pavlov's doodling dog. Whenever you define something, automatically you check the existence and uniqueness of what you have just defined. So what was the lesson given these definitions? First, as we've seen in the Cauchy distribution, even the mean value, mean value may not exist in some random variables. And as we see here in the central moments, if the mean does not exist, the central moments does not exist. And Cauchy distribution does not have the mean value, does not have the variance. Got it? And also, these numbers are scalars. And as we've seen in Gaussian distribution, the mean and variance are very, very popular to parameterize the distribution. However, many family of distributions have parameters more than two, or sometimes you need all the moments to fully characterize a distribution, assuming they exist. So just taking only a few of these moments are not enough to characterize a random variable, even though our myth says that mean and variance are enough. For example, mean, the expected value, gives us where is the center of mass. That may sound okay. What is the variance? Usually it is said that it represents the dispersion of the distribution from the mean. Or you may say that the standard deviation is a metric to show the dispersion. But as I told you, we may use the first order absolute central moment to represent the dispersion from the mean, as I asked the teacher when I was a middle school student. It's no problem. However, the reason why we love using variance and its square root standard deviation is because of the Gaussian distribution or normal distribution, because it has the one of the parameter same as the variance. Got it? So in some parallel universe where we may have some universal constant different from our universe, those aliens may using centralized absolute moment to parameterize their distributions. Anyway, so today we are going to study 3.2.3 section. This is very, very interesting and important and gives us why these moments are useful and why these are so powerful. So last time I briefly showed you this log-log plot, and you already have the exposure to this idea, but let me be a little bit redundant. So here goes the CCDF over random variable x. So what is a CCDF? CCDF is complementary cumulative distribution function. So if we call capital F sub capital X of X as the CDF of random variable, CCDF is defined as 1 minus CDF. And by definition of the CDF, which is the probability of event that capital X less than or equal to X, the CCDF precisely means probability of random event that random variable X strictly greater than the variable X. Unfortunately, our inequalities introduced today, they have a little bit different form. For example, let's see. Is this the CCDF? No, right? If we want the left-hand side to be CCDF, we should not have this equality. So strictly speaking, the inequalities we are going to study today are not bounding the complementary CDF in some sense. However, we know from the countable additivity, this is always true, right? Since the event that capital X is greater than or equal to A includes the event X greater than A, so our CCDF, so you may say self-additivity or union bound, this upper bound on the probability also upper bounds the CCDF. So it is not that wrong, okay? But let's be a little bit precise. Anyway, another thing is that suppose we have interest in the CCDF of a continuous random variable without any point mass. In that case, CCDF is continuous. So including some specific point or not doesn't matter because there is no point mass, right? Your probability of event that this should be same as that if there is no point mass. So it's okay somehow. So just for simplicity, let's say that today we are going to study 3 bounding techniques to upper bound CCDFs. Got it? And what is the shape of ordinary CCDF of a random variable? It looks like that. Why? If we assume no point mass at plus infinity, CDF must have what? At infinity, its value is 1. Precisely speaking, if x tends to infinity, so in engineering term, for sufficiently large value of x, CDF of x evaluated at a sufficiently large x is very, very close to 1. What does that mean for CCDF? CCDF evaluated at a sufficiently large x is very, very close to 0. Another thing is that CDF, by definition, is monotonically increasing. What does that mean? CCDF not only goes to 0 as x tends to infinity, it must be monotonically decreasing, right? So it's decreasing and goes to 0. It cannot be negative, right? Because it's probability. So you have some shape for sufficiently large x. The CCDF is a decaying and converging to 0. Now, the 3 inequalities are going to upper bound this CCDF. And let me show you where it is. I remember I drew it. Okay. Anyway, yeah, I will draw it later. Anyway, so what we are going to do is that we are going to upper bound this CCDF. What does that mean? We are going to plot some function like that and say that this CCDF is below this function. Got it? And some of you may say that, what's the purpose of that? The purpose is here, written in Korean, because I believe, even though I do my best to clearly speak in English, but you may better understand what I want to say. So what's the meaning of CCDF? Evaluated some value X. Probability of event that random variable generated is greater than or equal to that number. So if we set some number, we are expecting outcome greater than that value. So in many cases, we may interpret CCDF as what? Some rare events, very large value. We are interested in that event's probability. And we know that from this shape, that probability is very small. How small? We want to roughly say that it's less than, for example, 10 to the negative 5, 10 to the negative 6, 10 to the negative 7, something like that. Got it? So we want to bound the probability event that a very, very large number occurring. Got it? In financial signal processing, it may be your loss. You have some algorithm, you have some rule to invest your money on stock market, and you do some computation. And you want to roughly have what? The probability of the event that your loss is greater than $1 million, something like that. And then you want to find out your algorithm or your rule to invest gives you some upper bound. So probability of that event occurring within my lifespan is upper bounded by 10 to the minus 6, something like that. Got it? Now, we have an amazing results like this. First thing is so-called Markov's inequality, or if you really hate using apostrophe S, then the Markov inequality. The Markov inequality. And let's see. This is the CCDF of what? Of random variable X. But Markov inequality is for a non-negative random variable X. What does that mean? The probability of event that the random variable X greater than or equal to 0 equals 1. So in probability sense, with probability 1, you never observe non-negative outcome. Given that assumption, and we need one more assumption actually. As you see here, this inequality involves expected value of X. What does that mean? If the non-negative random variable X does not have the mean value, this inequality is useless. So we assume here two things for the Markov inequality. Random variable is a non-negative random variable, and it has the mean. Its mean exists. Then we have something amazing. And when I first saw this one, I couldn't draw it because I usually drew the CCDF as a function of X. So let me rewrite this one. Probability of event that capital X greater than or equal to X is upper bounded by expected value of X divided by X, right? For all x positive. This is the Markov inequality. And what does that mean? Now let me draw what I wanted to draw. So here goes the CCDF of x, right? Because we have this one, right? The CCDF is upper bounded by 1 and lower bounded by 0, monotonically decreasing, and goes to 0, assuming no point mass. Now, what is the right-hand side? You know the shape of this function from your middle school, right? It looks like this one. And let's say this is y, then you have y equals mean of x divided by x. What does this Markov inequality mean? You must have your CCDF where? Here. Your CCDF cannot go over this bound. Something's very strange. I told you that every random variable has different distribution. Now, what we are saying here is this one. Suppose our mean value is 5 for some non-negative random variable. So here is the set of all real random variables, and you have a small set. Probability of x greater than or equal to 0 equals 1. So it's non-negative with probability 1, and expected value of x is 5. Then there are many uncountably infinite number of random variables enclosed here, right? I can give you uncountably infinite number of non-negative random variables with mean 5. All of them have their CDFs appearing here. Got it? As far as they have the same mean value, and as far as they are non-negative random variables, their CCDF may have little bit different shape, but they are bounded by this inverse linear function. Amazing inequality, right? As far as you just have two facts, non-negativity and the mean value, you can bound the CCDF. You can bound the probability of very rare events using very simple formula. That is the Markov inequality. And let's see how to derive it. The Markov inequality is derived by drawing two curves or two lines, two functions graph in the xy plane. The first one is x divided by a. And this is x-axis. And the second one is the unit step function shifted by a. So u of x minus a. Now, for x greater than or equal to 0, for this reason, what can you say? This curve, right? This is x over a, is always greater than or equal to this unit step function. Am I right? So you can say that for all x greater than or equal to 0, u of x minus a is upper bounded by x over a. Now, you multiply the probability density function of x, assuming PDF exists, then what happens? Here, you multiply the density function of x, and this inequality does not change. Why? Because the PDF is a non-negative number always. So if you multiply non-negative number to both sides of the inequality, the direction of the inequality does not change, as you learned in middle school math. Then you integrate from 0 to infinity. No problem, right? Because for each integrand, you have the strict the inequality. Now you apply that inequality, uncountably infinite inequality, in this integration. So you have this result. Now, what is the right-hand side? Right-hand side is simply what? By the fundamental theorem of expectation, capital X divided by A, right? Value times probability. What is the left-hand side? This is a little bit tricky, but this U of X minus A gives you what? You can change the lower limit of the integral from A to X. Then what do you have? This is probability of event that X greater than or equal to X, right? Because this is here. Got it? So you have the inequality. Of course, due to the linearity, you can take 1 over A out. That's what? That's the Markov inequality. Here we assume A strictly positive because otherwise it's this strange shape, right? We don't want that. So we assumed A positive, and then we have this result. Now there is a slight trick we can use. What we can do is that we replace A with some K expected value of X. Then what happens? The right-hand side has what? Left-hand side is simply K mu X. The right-hand side is what? 1 over K. Okay. So if you just have interest in the probability of event that X greater than K times the mean value, then it is upper bounded by 1 over K. K can be some natural number. It can be any positive real number. It's amazing, right? We only know two things. It's non-negative random variable. It has mean mu X. Then we can bound the rare events probability using a very simple inverse linear function. Now, we want to little bit generalize this one, removing the non-negativity assumption on the random variable. We want to have some bounding technique applicable to all random variables, not just the non-negative random variable. So what we do is this one. Let me just use this one. This is for Chebyshev or Chebyshev or Chebyshev. I don't know the exact name, but anyway, Chebyshev inequality. And from this first example, many of you immediately got the idea. Suppose that you have X minus X bar divided by sigma, not sigma, epsilon. Not yet. Square. This is parabola, right? Located at X bar. And then what happens? If this function evaluated at X bar plus minus epsilon, then what do you have? You have 1, right? So this function with height 1, that function with height 1. So this function, right? Lower bounds the parabola. Got it? Let's say this function as g. Then you may say that g of x lower bounds this one. Now again, what we are doing is that we multiply the density function of x and we integrate to have the inequality that involves moments. In Markov inequality, we wanted to extract the mean value. Now, what do we do? What is the left-hand side? Left-hand side is probability of event that x minus x bar greater than or equal to epsilon. And what is the right-hand side? Expected value of x minus x bar divided by sigma squared. So you have epsilon squared. So you have epsilon squared in the denominator, and you have the variance of x. So in this derivation, now you have not only the mean value of x appearing, but also the variance appearing here. So can you apply this inequality to every real random variable? No. We can apply this not just for non-negative random variable, but these random variables must have finite mean value and finite variance. Got it? So it's a little bit generalized, but it is also a little bit specialized. Got it? Now, again, we can choose epsilon a little bit strangely. So let's choose epsilon as k times sigma x. So k times the standard deviation. Then what happens? We have this is what? X minus x bar divided by sigma greater than or equal to k. Why do I divide by k both sides? Because I love z-scoring. So I want to subtract the mean and divide by the standard deviation. What is the right-hand side? You plug in that one here. Then amazingly, now you have inverse of k squared. So this Chebyshev inequality gives us what? Gives us some bounding technique related to something proportional to 1 over x squared. And you may just say this one, okay, if you want. Okay. So the difference is that before our upper bound was inverse linear. Now it is inverse quadratic. Which one converge to 0 faster? 1 over x or 1 over x squared? 1 over x squared. So we have much faster converging upper bound to 0. So we can bound the CCDF more faster. Now, here goes the third inequality, Chernoff inequality, or the bound obtained by Chernoff's inequality is called Chernoff bound. And the difference you can immediately see. Here you have u of x minus a, again, the unit step function. Now, you are bounding this unit step using e to the nu, this is Greek letter nu corresponding to n, nu of x minus a, assuming nu is positive. That's why you have increasing exponential function here. Otherwise, it's confusing, right? Now, you have the inequality. That's what? U over x minus a less than or equal to e to the nu x minus a. Again, what we do is that we multiply the density function of x and integrate all over the entire real line. Or if you really hate, you multiply dCdF of x dx, right? The dCdF of x then integrate. Anyway, then what do you have? The left-hand side is again becomes x greater than or equal to a, the tail probability, right tail, precisely speaking. What is the next one? This one, you can factor e to the negative nu a, and you have e to the nu x. But see that if you fix nu, what happens? This is a constant, right? And what is this one? This is a function of a. Now, let's replace a with x. Then what happens for Chernoff inequality? Chernoff's inequality gives you what? Gives you exponentially decaying upper bound. This is proportional to e to the negative nu x. Now, let me ask you a question. Which one is faster in decreasing? 1 over x, 1 over x squared, or e to the negative some positive nu x? Which one decays faster? Of course, this exponential bound. Why? And here goes something interesting. This proportionality constant is interesting thing. As you know from the calculus, this exponential function with real valued exponent is one of the transcendental functions, 초월 함수. And these transcendental functions can be written as what? Written as Taylor series. And you have this one. Now, again, let's multiply density function of x and integrate. What happens? You have the expected value of nu capital X. And what is the right-hand side? If it converges and all the moments exist, then you have this one. So if you fix nu, what happens? This is some constant, and this is the sum of constants times the case moment of the random variable x. And when can we have this value finite? Since k factorial increases very, very fast, as far as all the moments exist, then we have a finite number. Of course, even though these are not finite, for nu equals 0, it's always 1, right? For nu equals 0, it's always 1 by definition, right? If nu equals 0, then this is 1. Expected value of 1 is 1. However, that case is not useful. When this Chernoff inequality is useful, usually nu is a strictly positive number. What does that mean? Then this expected value of e to the nu x includes all the case non-central moments. That's why you have that so fast converging upper bound. Of course, some of you already have an idea. Hey, Markov order 1, first order, Chebyshev order 2, and I may use the third order polynomial, the simplest one, x to the raised power of 3, to upper bound the negative function as we did for Markov inequality. And in that case, probably I have 1 over x cubed upper bound. Hey, I can find my named upper bound. You're right. And fourth order, fifth order, sixth order, any order, actually, you can derive. Got it? And what if all the moments exist? Then you have this bound. Now, let's see the differences between these three inequalities. in the log-log plot. Then, as we've seen last time, this -1 slope in log-log plot. So 1 decade decrease requires 1 decade increase in x. Here, decade means 10 times, right? As you've seen in some log-log plot in signals and systems or circuit theory or electronic circuit. So this is what? The upper bound derived from the Markov inequality. And this is the inequality from the Chebyshev inequality. And you may draw many other upper bounds using your named inequalities if you want. And eventually, if all the moments exist, we can bound the tail probability using an exponential upper bound, which gives you a waterfall-like curve here. Got it? So do you see the difference? Anyway, these inequalities require the existence of corresponding moments. But amazing thing is that as far as we have the same moments, then we may upper bound different CCDFs using the same upper bound. That's very good. But be careful. As I told you, these inequalities are not applicable to some distributions. For example, you want to apply Markov inequality to Cauchy distribution. You can't. Got it? You cannot apply Chebyshev inequality or Chernoff inequality to Cauchy distribution. Anyway, so we are done. And here goes one of the famous upper bounding technique by the Chernoff inequality. Once I told you the Q function. What is the Q function? It's 1 minus the phi function. What is the phi function? Phi function is the CDF of standard normal distribution. You remember, right? So Q function is a CCDF. Now, this CCDF has this strange shape, and it cannot be derived using elementary functions. So we usually tabl화하다 this Q function, or we make approximation. We derive upper bound. Oh, upper bounds. So let's try to upper bound this Q function using Chernoff inequality. So what we do is this one. We know that from here, what we need to find is what? Just simply this function, expected value of e to the nu x for x standard Gaussian. And actually, it's not difficult. If you take a look at the Wikipedia page for normal distribution, you have this coefficient. Very simple. E to the nu square divided by 2. Actually, you can just show this using high school integration. So we have what? We have for standard Gaussian x, the CCDF, this is the Q function, evaluated at A, upper bounded by this one. For any nu positive. Got it? For any nu positive. The problem is that, hey, why we still have a nu? And here goes one idea. So actually, Chernoff inequality gives us how many upper bounds? Uncountably infinite upper bounds. Why? Because we can choose the value of nu by any positive real number. Then which one would be better? You may minimize this one because it's coefficient. So if you minimize the coefficient to e to the negative nu x, the bounds reduce. So you can have tighter upper bound. So what do you want? One of the way is that you apply derivative and set equals 0. And suddenly, it's somewhat strange, but the minimizing new value equals A. So you substitute new equals A. And then suddenly you have this upper bound for each A. Be careful. Here, we are minimizing this right-hand side for each A. Okay, not for all A. But interestingly, for each A, you have new equals A. So you substitute u equals A and get this upper bound. Or otherwise, Q of X is upper bounded by e to the negative x squared divided by 2 for all x greater than or equal to 0. So Q function plotted in log x versus log Q of X is again what? Upper bounded by a waterfall curve. We know that Q of X has waterfall shape, and upper bound is also waterfall shaped according to our Chebyshev inequality technique. Got it? Anyway, there is one more inequality called Jensen's inequality, and many of you have seen it in your high school math class. And this assumes that there is a function g that is convex or concave. Then you have interesting inequality. When you change the order of a function and expectation, two operations, then you have inequality. Here, expectation, g of x comes first, and here, expectation operation comes first. And by drawing the graph g of x, and just assuming that you have only 4 possible outcomes, or 6 in this case, possible outcomes uniformly distributed, and you just calculate the mean value. And suddenly you find that g function evaluated at x bar, that is this height, is always less than the expectation of g of x for a convex function. And the exact opposite holds for concave function. This is Jensen's inequality, and one of the famous and well-known application of Jensen's inequality is this inequality. Second order non-central moment is lower bounded by the squared mean. Why? Here we assume that x squared is the parabola, is the function g, which is convex. Then we have the result. Of course, since the variance of x is what? Expectation of x squared minus expectation of x squared, and variance by definition is always greater than or equal to 0, we have the same formula. However, Jensen's inequality also gives us this famous inequality. By the way, we may upper bound the CDFs, lower bound the CDFs using these inequalities. Okay, so we've just finished it, section 3.2. Up to 3.2, we were interested in what? In computing the expected value of a function of random variable. And representative functions of random variables are polynomial functions. So we have moments. And we've seen inequalities, 4 inequalities related with moments. Now, here goes one of the most important new definition. Unfortunately, many textbook does not talk about this one. But I really believe this is important. And here goes the title. functions that give moments. What does that mean? So what we are going to do is this one. Here is a random number generator. And here is a sum operator. And here we get a function. Got it? One is the function of omega, and another is function of du. And some of you remember, hey, we've already seen this one. Expected value of e to the nu x. Yes. And this function we've seen in our Chernoff inequality is named as moment generating function. Moment generating function. Got it? And what is this one? This one is defined as e to the j omega random variable x. So they look very similar, but be careful. Omega is real and u is real. So actually, they are two different functions, cannot be interchangeable. Because here, the exponent is strictly real. U is real, x is real. In the above, the exponent is pure imaginary. But mathematically, they are very, very similar. When both of the functions exist, then from one, you can find the other. When? When both functions exist. So whenever I define something, I have a habit of talking about existence. What does that mean? One of these functions or all of the functions may not exist for a specific random variable such as Cauchy distribution. An amazing result is this one. This first function is characteristic function of random variable x, always exists. The second one, the moment generating function, does not always exist. So which one is more fundamental? The characteristic function. That's why this function is called characteristic function. What do you guess? Definitely this characteristic function characterizes the random variable x. Yes, your guess is correct. So amazing result is this one. Given a random variable, any random variable, it has its characteristic function. And as far as you know this function of omega completely, you know this distribution completely. That's why this function is called the characteristic function. Got it? Now let's see the definition of the characteristic function. Characteristic function is written as phi sub capital X to specify this is the characteristic function of random variable x. Got it? And it's a function of omega, as the name says. And it's defined as expectation of e to the j. Here j is the square root of -1 and omega times x. And omega is real. And as our expectation, the fundamental theorem says, this one can be rewritten by using the probability measure. It can be written as the argument of this absolute value function. So this is the same. Of course, you can define it using the CDF like this, right? Or if the density function exists or probability mass function exists, you can define the characteristic functions in these ways. Now, let's show or prove why this characteristic function exists for all random variable. By the way, when you transform a distribution or PDF or CDF into a function and it exists, what does that mean? its value is finite for all x in the domain, for all omega in the domain. So what you want to show is that this phi sub x of omega exists for all omega. And one of the technique is to take the absolute value. And due to the triangle inequality, you have this inequality here, and you can change the order of absolute value and integration. Then what happens? Because e to the j times real is always 1, you have 1 times the probability measure integrated for all s. What is that? It's 1. So you have always 1 that upper bounds your function. What does that mean? Your function is finite, always. Got it? So your characteristic function exists for all value of real omega. Got it? And we haven't yet proved why this fully characterizes the distribution. We have just shown that it exists always for any random variable. And we need actually a deeper knowledge, but let's, for simplicity, assume that the PDF exists and take a look at the characteristic function carefully. What is it? Actually, you've seen something similar in signal-gen systems. Suppose you have a continuous time function x of t, and you multiply e to the negative j omega x and integrate omega t. And dt, what do you have? You have the Fourier transform of x of t as a function of radian frequency omega. Now, let's compare them and what is your result? Hey, characteristic function is the Fourier transform of the density evaluated at negative omega, right? Because we have the difference in the sign. So it's a Fourier transform, simply put. And in some cases, inverse Fourier transform exists, right? And we have our original signal back. What does that mean? We know that, as we've proven, see, this characteristic function exists for all random variable. And if the inverse transform exists, what happens? From this characteristic function, you can find the PDF. That's it. Of course, PDF may have direct delta functions, and mathematically speaking, may not exist. So actually, we need a higher level mathematics to prove that this characteristic function really invertible somehow. That is not covered in this course. And if you read the note, Levy integral, blah, 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 is there. Got it? But anyway, in the simplest case, inverse Fourier transform gives you the PDF back, which means your characteristic function contains all the information about your probability distribution. Levy's integral formula, blah, blah, blah. Got it? So characteristic function is very interesting thing. Now, let's summarize how many ways exist to characterize a random variable. This is a good time. The first one is what? The probability space and the measurable function. That is the most fundamental method to fully characterize a random variable, right? What is the second most fundamental one? You derive the induced probability space. What is the third one? You use the cumulative distribution function, which is equivalent via Borel set and Borel sigma algebra to the induced probability measure. the fourth one is what? The characteristic function. So as far as you fully know the information about the characteristic function for every omega, then you know exact distribution of the random variable. Now, let's see another one, moment generating function. Sorry, before talking about that, our title said what? Our title of this section said functions that give moments, not characteristic function, which means that from the characteristic function, we can find the moments if it exists. And this theorem is very interesting. What does this theorem says? So here is the characteristic function of x as a function of omega. So if you apply derivative, you must apply derivative with respect to omega, the real number. So what is this one? Nth order derivative. And where it is evaluated at omega equals 0. Then you little bit scale it, and amazingly, you get the nth order non-central moment of x. Why? One of the simplest but white lie type proof is this one. Suppose you have this definition and you apply nth order derivative. And let's assume that you can change the order of derivative and expectation. Then what happens? You have jx raised to the power of n. Am I right? E to the j omega x. Due to the, am I right? Yeah. And now let's evaluate. Now let's evaluate this one at omega equals 0. Then what happens? You have jx raised to the power n. And what is this one? Omega equals 0, 1. So if you compute the nth order derivative of the characteristic function, then you have j to the n and the nth order non-central moment. If you can apply derivative. Why do I say that? When I first heard my professor emphasize this one, I got confused. Hey, professor just said characteristic function exists for all omega. Yeah, professor said characteristic function exists for all omega. He or she didn't say that it's differentiable. Got it? For every random variable, you have the characteristic function well defined around omega equals 0. However, that does not mean you can find nth order derivative. Now you know the example, very good example called Cauchy distribution. And let's see what happens. The Cauchy distribution has very strange characteristic function. And here it is. This is the characteristic function of the Cauchy distribution shifted by x0 and scaled by gamma. And as you see here, in the exponent, you have the absolute value of x. Suppose you plot this one with setting x0 equals 0 to make it real, then you have this function. So when x0 equals 0. This is the characteristic function of the Cauchy distribution. Now, as you see here, it's not differentiable at omega equals 0. That's why, even though Cauchy distribution has well-defined characteristic function, it still does not have even the first order non-central moment because it's not differentiable at omega equals 0. Got it? Now, it's time to move on to the moment generating function. Moment generating function in its form is very similar to the characteristic function, except that the exponent of the exponential function is always real, unlike the characteristic function, where it was always pure imaginary. Now, this function may not exist for some nu. And you may have seen something similar. The first one is that using CDF, we can write the moment generating function in this form. And also, if we have the probability mass function or PDF, then we have this nice form. Now let's take a look at this last case. You've also seen this formula already, not only in signal gen systems, but also in circuit theory. It's bilateral Laplace transform with sign change. And whenever you talk about Laplace transform, what do you need? You have, by the way, in Laplace transform, our exponent can be any complex number. But in moment generating function, we restrict nu to real. That's the difference. So actually, you can say that the moment generating function is the Laplace transform evaluated on the real axis. Got it? Now, let's take a look at the figure I have drawn. What is the integrand? It's the product between the PDF and the exponential function. If nu is real, and since x is real, depending on the sign of nu, you have ever increasing exponential function or ever decreasing exponential function. Now you multiply these two and integrate over all x. What may happen? If the tail of the PDF does not vanish faster than e to the nu x for positive nu, your integral may not exist. Got it? That's why the moment generating function may not exist for some random variable, unlike the characteristic function. So fundamentally speaking, you must talk about the reason of convergence. You really hated this one when you learned the Laplace transform. But anyway, let me skip. You know what it is. Again, here is a very naive theorem. Moment generating function generates moments. How? Actually, it's simpler because suppose we have the nth order derivative of the moment generating function with respect to nu. What will happen? If we can interchange the order, then we have e to the nu, e to the x raised to power n, e to the nu x. So if we evaluate this one at nu equals 0, then we have the nth order moment. So moment generating function really generates moment. For any n? No. Again, we need differentiability of the moment generating function at nu equals 0. If first order derivative is not possible, mean does not exist. If the second, even if first order derivative is possible, but second order derivative is not possible, the second order moment does not exist. Something like that. So here goes a table that summarizes the characteristic functions and moment generating functions of famous distributions. So in the upper rows, we have discrete random variables you've already seen, and here are continuous random variables. And we have characteristic function and moment generating function, characteristic, moment generating character. And you've seen it already. Hey, by replacing j omega with nu, they are the same. When? they exist, right? Got it? See that here? We have strange row that says does not exist. This is what? The Cauchy distribution. Got it? So Cauchy distribution is very good example to talk about something does not exist. And some of our naive belief fails. Got it? Now I have 5 minutes and I will finish it, section 3.3, and we move to the next section. I'm happy in that sense. So what we are going to do is that not only computing the output expected value, we want to characterize the output. What does that mean? We want to find the CDF of the output random variable, or we want to find the characteristic function of the output random variable, or we may want to find the induced probability measure of the output random variable, blah, blah, blah. How? How? I still remember when I saw one of the final exam problems in this course when I was at your position. I studied the entire textbook very carefully and sit on the chair to take the final exam. And in the first problem, it was a question about computing the expected value of a random process, actually. You are not yet taught. And I had no idea how to compute it for a while. I was frozen. Almost the same thing happened when I first saw this one. I just said that, hey, I know everything. All the moments say blah, blah, blah. And suddenly professor says that, can you fully characterize the output? How? Even though I studied very carefully, I forgot it at almost everything related to this one when I was taking the final exam. So I pondered over how to teach you. So here goes the preview of what I want to show. Suppose you have a Gaussian, okay? A Gaussian random number generator. And here is your very simple function. This is called affine function, or affine 변환 in Korean. I don't know why they just say affine, but anyway. If b equals 0, it's really linear, right? Now the output is y, that is g of x. Let's assume a is positive in this case. And b is also positive. Got it? So this straight line is y equals ax plus b. Now, what happens when you generate many x independently from this random number generator? This idea exactly is parallel to our idea of understanding our PDF. I asked you to draw a normalized histogram. You remember that? And consider limit of your normalized histogram. We are going to do is the same thing. We are going to do is just generate a lot of value of x. Okay, not yet. And let's see what happens. Suppose this is generated, this dot is generated. Then what is the output? Output is simply this height, so this value. Got it? What about that dot? These dots are mapped here. Now, what if a is greater than 1? What will happen? Our original Gaussian distribution may be more dispersed, right? Do you have the idea? If a is greater than 1, so the line becomes steeper, what will happen? Our output is more dispersed than the input. This is one of the key idea to understand the entire section 3.3 next week. Okay, that's all for today.